Okay, hi again everyone. Professor Sebastian. We're in our Calculus 3 class notes, and we are now moving into section 13.3 of chapter 3, which is determining arc length in space. We are on page 32. Sorry, we're on page 32. And here's a definition. The length of a smooth curve, r of t, equals x of ti plus y of tj plus z of tk, where t goes from a to b, that is traced exactly once as t increases from t equals a to t equals b is this formula. This should look very familiar to when you looked at parametric equations in Calc 2. You just had the two components, x of t and y of t. Okay, so now that we have a third component in the k direction, we just add that piece in there. So dx dt quantity squared, dy dt quantity squared, dz dt quantity squared, take the square root. You have to integrate that and then evaluate from a to b. So notice though that that is simply the magnitude of the velocity vector, because remember the velocity vector is r prime of t, so these would be the components of r prime. Okay, so it's the magnitude of velocity evaluated from a to b dt. So for example, let's say we have a hang glider soaring upward along the helix. R of t equals cosine of ti plus sine of tj plus tk. So here's a visual of our helix. Put some dotted lines here to represent that that's going behind the z-axis, spiraling upwards. How long is the glider's path from t equals 0 to t equals 10 seconds? So note it takes 2 pi to get all the way around once as it's still climbing. So 4 pi as it get all the ways around once here. So 4 pi is about 4 times 3-ish, right? About 12 seconds. So before we get there, it didn't get all the way around a second time. About 10 seconds. I don't know. Who knows exactly? Somewhere in here. Just wanted to give you a visual of it. But to actually compute that arc length of this curve from t equals 0 to t equals 10, we integrate its speed, dt, from 0 to 10. So the speed is, right, velocity, take the derivative of each piece. So the derivative of cosine of t is minus sine of t. We square that. The derivative of sine of t is cosine of t. We square that. The derivative of t is 1. 1 squared is still 1. So I get sine squared of t plus cosine squared of t plus 1. Unfortunately, sine squared of t plus cosine squared of t is 1. So that's 1 plus 1, or 2. So the square root of 2 from 0 to 10, very easy to evaluate. So I get square root of 2 times 10 minus 0, right, when I evaluate this using the fundamental theorem. So it's just 10 square root of 2. Now note, if we choose a base point P of t naught on a smooth curve C parameterized by t, like we have here, each value of t determines a point, P of t, which is x of t, y of t, z of t, on that curve C, and a directed distance, which is also known as the arc length parameter, with base point P of t naught. Okay, so let's say it's just any general curve. I'm trying to draw a general picture here. So I'm going to start right here as my base point. That's actually the starting point of the curve. Now, I actually want to parameterize this curve not with t's, because t is the time it takes to travel along that curve. I want to parameterize it with a quantity called s, which is the distance along the curve. So what is s? Well, since we learned how to find arc length, it's simply this. Now I'm going to integrate with respect to a dummy variable tau, let's call it, because I need to integrate from t naught to t. So I can't have t's in here. It wouldn't make any sense. So I just use a dummy variable tau, but it's still just the magnitude of the velocity, but using the dummy variable tau to integrate. So this is what s would be. And then I could parameterize my curve in terms of s instead of t. So as an example, let's see how that would work. Actually, I'll come back and do another video on this.